So here's the equation we were working on in the last set of the recordings. So in the number 2 recording of the evolution of populations. I'll just read it again so that we can go over it and then start to set it up for you. In a population of 200 mice, 98 are homozygous dominant for brown coat color, 84 are heterozygous, and 18 are homozygous recessive. So again, like I said before, it sets up the problem for you already with your total, so that's nice. You don't have to find your total. Get rid of those. Okay, so there's your total. And then what we need to do is find the allele frequencies. So we need the P and the Q frequency. Remember how we did that in the last presentation? We need to find all the total dominant alleles and all the total recessive alleles, and then divide those by the total alleles altogether. So if 98 are homozygous dominant, that's what we are showing right here. Okay, 98 are homozygous dominant, and each of those is, for example, I said big B, so it's got 2 big B's, so times 2 for every one of those alleles. So we actually are going to take 98 times 2 to get what our total homozygous dominant alleles are for those particular brown mice. So I'm just going to pull up a calculator here real quick, and we're going to see what we've got. So we're going to take 98 times 2. It's a total of 196. Okay, so 196 there. Then we've also got some big B's in our heterozygous individuals, right? So 84 are heterozygous, and each of those only gives 1 big B. So we're going to add 84 to our 96. Again, we're just trying to add up all the total big B mice alleles. So that's 280. All right. So go back to our what we were looking for here, and we said that we wanted to know what the P allele was. The P allele is the total number of dominant alleles. So again, we're at 280 divided by the total alleles in the population. Well, as I said, we got 200 mice, which means each of those has 2 alleles, right? Each of those has 2 big B's. So that means we've got a total of 400 alleles in the population. 200 times 2, 1 for each of the B's. So we're going to do that on our calculator. We're going to take 280 divided by 400. And our total is 0.7. So our p-value must equal 0.7. All right, so got the little p figured out. Now we need to find the Q, which is the homozygous recessive allele frequency. So we're going to do that next. The Q allele is found in the same way. We have to add up all the little b alleles this time. So Q is going to be all of our little b alleles. We've got 18 that are homozygous recessive, and they each have 2 little b's. So we're going to take 18 times 2, which is 36. Plus the little b alleles that we find in our heterozygous individuals, each one of those giving 1, so 84. Let's go on our calculator. We'll do 18 plus 84, or sorry, 36 plus 84. $120. So 36 plus 84 equals 120. And then divide that by our total alleles, which remember was 2 times 200, so 400. And so we'll do that on our calculator. 120 divided by 400. Oops. There we go. Equals 0.3. So again, Q equals 0.3, or 30% of our population is recessive alleles. And now that should make sense because remember we said that P is equal to 0.7 and together they make up the entire population, right? 0.3 plus 0.7 is 100%. The alleles have to be either dominant or recessive, so that's our whole population. Alright, so Q is 0.3, P is 0.7, those are allele frequencies. Ready to move on to the next part of the problem. Okay, the next part says we want the genotype frequencies. So the genotype frequencies are going to be the variables in your Hardy-Weinberg equation. So P squared, Q squared, and 2PQ. Alright, so let's just keep this up here as a note. P equaled 0.7 and Q equaled 0.3. Get my decimal point there. Okay, because we're going to need to use those now to figure out the genotype frequencies. So if P is 0.7, then P squared should be pretty easy to figure out. You would probably do this in your head, but I'll just show you on the calculator. So 0.7 times 0.7 equals 0.49. Okay, so we're going to put that in. Okay, so 0.49. Do the same thing with our Q value. Okay, our Q squared, to find that we need to take 0.3 squared. So I'll just do that on the calculator here quick. 0.3 times 0.3 equals, oh, something went weird. Try it again. 0.3 times 0.3 equals 0.09. Okay, so our Q squared value is 0.09. 2PQ is 2 times P times Q. So 2 times P is 0.7 times Q is 0.3. Again, I'm sure you can do this in your head, but let's just do it on a calculator for fun. So we've got 2 times 0.3 times 0.7, there's your P and your Q, equals 0.42. Okay. So those are all the allele frequencies. Remember that the P squared equals our homozygous dominant frequency. So 49% of our population is homozygous dominant. Our Q squared equals our recessive, homozygous recessive genotype. So 9% of our population is homozygous recessive. And our 2PQ equals our heterozygous genotype. So 42% of our population is heterozygous. And again, all of these are very close to adding up to 100%. All right, on to the last question. Down here on number 3, it states, what are the genotype frequencies of the next population if equilibrium is maintained? In other words, if no evolution takes place, what is the expected frequency of our genotypes in the next population? Well, if no allele is better than another, if some don't survive better than others, they're all the same. Remember that random mating is occurring, no mutations, no immigration, emigration, no natural selection, then the genotype frequencies are going to stay the same. Okay, that just means simply that no evolution is taking place. We'll do some more of these problems in class for practice, but I wanted to give you one chance to kind of see it at your own pace. So if you need to, go through it a couple times and make sure that you fully understand it before we get to class and start working on those problems.